emails.
Anybody sitting here?
All right, thank you. Oh, also, just so you know, if you want to watch from this, I'm going to set up a video camera, but it's not going to record Yeah, if only were 2 ways, that would be great.
You want to start doing these in entertainment?
Apparently.
Chairs over up there. So this is. Okay. So we want to introduce Vanessa Bailey, who's going to defend her PhD. Vanessa is going to give an overview of the research she's done. We can have questions, but this is an examination, and so I reserve the right to get off a question and get started to get into sort of a student examination kind of question, or push us off schedule. But I doubt that that will happen, since Vanessa has graciously agreed to make this talk very short.
Try my best.
So, go for it.
All right. Well, thanks everybody for coming this morning. I'm really excited to talk to you about the work I've been doing over the last 6 years on adaptive optics for the LDT, and specifically targeting planetary systems with adaptive optics. So before I get started, I want to thank a number of people, all of my scientific collaborators and mentors. You've helped me build these projects, you've given me advice, you've helped me develop as a scientist, so thank you. To the instrument teams, thank you for building wonderful instruments. I couldn't have done this without you. And as well as to my friends, my family, all of you here, thank you for helping me along the road to get here today. So when I started grad school 6 years ago now, it was a really interesting time to be joining the exoplanet community, because we only had a few examples of directly imaged planets. It was only a few months before I started grad school in my last year in undergrad, basically, that we discovered the first directly imaged exoplanetary system, HR8799. Now we know it has 4 planets, not just 3, but in this discovery image, we only knew 3 at the time. So these are very massive super Jupiters orbiting at tens of AU, which are very unlike anything in our own solar system. Certainly, many of these different planetary detection techniques are telling us that our solar system architecture is not unique. And you know, it's only because of these powerful new technologies that we're discovering new kinds of planets and new kinds of planetary systems. And not very long after I started grad school, I found the second sort of bona fide planetary system. The Beta Pic system here is another giant planet, super Jupiter, orbiting sort of around Saturn's orbit, more or less, within a debris disk. And one of the things I was interested in understanding is how can we do a better job of finding these planets. And if you notice, just in these first 2, there's a commonality, and that's that both of these systems have bright debris disks. So in the case of the Beta Pic system, it's been directly imaged. Here it's just an edge-on disk. The planet is warping the disk. It's very at the radii close to its orbit. For HR8799, we haven't imaged the disk, and these are all debris disks. We haven't imaged it because it's just too tenuous to see in direct imaging so far. But what we do know, based on spectral energy distribution analysis, is that the HR8799 disk has two components, a cold outer component and a warm inner component, and the planets reside within the gap between those two disk components. And so this is what we expect from the canonical picture of planet formation, star formation, where you have a cloud as it collapses to form a star. When you preserve angular momentum, you end up driving a protoplanetary disk. It's very gas-rich and dust-rich, but as the disk evolves, feeding material onto the star or growing planets, in this process, the gas dissipates over a few million years, the grains grow together to become planets, and what we expect to be left over with are these sorts of debris disks that are mostly just small grains, medium-sized pebbles, and planetesimals, not very much gas left. And the really nice thing about having a gap system like this, where you have planets that are carving a gap in a debris disk, is that it shows up in indirect indicators. You don't have to image it directly. And that's evident here from the SED of the HR8799 system. So what we're looking at is, as a function of wavelength, and sort of mid-infrared, we're looking at the flux of just the disk. So this is unresolved spectroscopy and photometry of the system, but we've already subtracted away the stellar flux. So this is the SED of only the disk, and all the SEDs I'll be showing you today are only the disk. So what you can see is that we have sort of the spectrum here in green points from Spitzer, as well as Herschel here at the longer wavelengths. And for a continuous debris disk, with material at all radii from close to the star out to tens of AU, you expect an SED to look something like this, relatively continuous, from around 10 microns out to 100 microns. But you'll notice, probably, that there's this deficit of material here at sort of 20 to 30 microns. And what that's indicating is that there's a deficit of material that would emit at those particular wavelengths. In other words, there's a gap in this disk. So what we can do to figure out where the gap is to model the SED. We start by fitting temperatures, more than black bodies to the SED. That's the first step, the simplest fit. And you can see that this is well fit by roughly 45 Kelvin black body plus 150 Kelvin black body. And this only gives you temperature, of course. It doesn't give you location. So to map temperature to location, you have to make some assumptions about the grain population that's making up this disk. So the simplest assumption is that they're all black body grains. They emit and absorb equally well at all wavelengths. And so this is the kind of canonical equilibrium temperature distribution that you, or equilibrium temperature point that you have to calculate in Astro 202. And so we can get a distance for black body grains, and it turns out that's the minimum distance this temperature ring could be from the star. And that's because for a more reasonable grain size distribution, the disk could be at a variety of locations. There's kind of a fudge factor. And that's because in a real disk, you have collisions between particles, grinding them down to smaller and smaller sizes. So you have a large population of sort of a few micron sized grains. And if you'll notice, the cold component of this disk has a peak somewhere around 100 microns, but 1 micron grains aren't going to emit 100 micron light very effectively. So they're going to be superheated. So the same temperature, for the same temperature grain, the small grains are going to be located farther from the star than a black body grain that can emit equally well at all wavelengths. This means that once we know the temperature, we know its location, but within a fudge factor of 2 or 3. But what isn't in doubt, even if we don't know the exact location of the gap, we do know there is a gap. That's irrefutable regardless of what properties you're assuming for the grain population. And this works quite well in the HR8799 system. So there are those 4 directly imaged planets. Here I'm showing you the star is here, radius is going outward to the right, and the cold component and the warm component very nicely bracket those 4 planets. You can see that the planets are sculpting that disk. So we thought it would be a good idea to build a survey using this principle. I wish I could take credit for that title, thanks, Phil. So what we're very much hoping is that if we have a population of SEDs that look like they have gaps or otherwise truncated in unusual locations, so here I've got my SED and sort of a cartoon of what that system might look like. What we're hoping is that if we use direct imaging, like with MMT, Clio, Niki, Magellan, VLT, one of these high contrast adaptive optic systems, then what we're going to see is a little point source here at a location that's consistent with sculpting the inner edge of that cold debris disk and clearing a gap. So I don't have a lot of detections to show you. Mostly what I have are contrast curves. So let's walk through those first. What we're looking at here as a function of separation from the star in arc seconds, going between about 1/2 and 2 arc seconds, is the noise floor of the data that we're taking. So the contrast with respect to the star. So we're getting somewhere between 6 and 12 magnitudes of contrast between the star and the background noise in this particular set of observations. And if we know the age of the star, the age of the system, and we assume some planetary evolution model, we can translate that contrast or that magnitude that this corresponds to into a planet mass. So in this particular case, that corresponds to masses between sort of 5 to 10 Jupiter masses all the way up to 100 Jupiter masses. And just to give you some perspective, the canonical separation between giant planets and brown dwarfs is the deuterium burning limit, which we think is around 13 Jupiter masses. Although frankly, this is a fuzzy distinction, this boundary, and certainly there are those who argue it's entirely artificial for various reasons. But it's a useful one to keep in mind. We think giant planets are around here. And the hydrogen burning limit, the thing that separates brown dwarfs from low mass stars, is at about 75 Jupiter masses up here. So in this particular case, now we can see what kind of sensitivity we get with respect to where we think the disk is for the system. So the black body location, that minimum inner separation for the cold component of this disk. So in other words, the outer edge of the gap could be as close as 1 arc second. And there, we're sensitive to something like 30 Jupiter masses. Because of that fudge factor, the outer edge of that gap could be a little bit farther out. It could be more like 2 arc seconds or so. And there we're sensitive to low mass brown dwarfs, a little bit closer to the planetary mass regime. And here, just highlighted the regime that we're sensitive to companions at for the range of disk properties that we might derive from SED. So now we can make contrast curves in the same sort of calculation for the various different data sets that we've taken. So we have Niki H-band data from Gemini South. We have Clio when it was on the MMT, Clio when it was on Magellan. We also used VLT and NACO, although that's been previously published by my collaborator Tiffany Meshkat. So I'm not showing them here. But let's look at the Niki contrast curves first. So what you can see is that typically, depends on whether we're looking at a disk where the gap is quite far away from the star or quite close to the star, we're usually reaching sensitivities that are planet mass, maybe brown dwarf mass in some cases. So we're saying that in this case, we could tell that these are all null detections. So there are no giant planets above, say, 5 Jupiter masses that are sculpting the disk in this particular case. And for the MMT Clio data, we get fairly similar limits for some of our targets, planets in brown dwarf mass regime. But for 2 of the targets, we were trying to push really aggressively to very small separations from the star because these were disks that were truncated quite close to the star. So we expected something to be sculpting the outer edge of a hot disk. And it's just true that because MMT is sort of a previous generation AO system, the contrast at 1/2 an arc second is only good enough to get us to low mass stars in these particular cases. But we did have at least one system where this technique worked, or we found something anyway. And so in this case, this is one of not one of the systems with a gap, but that had a disk that had an SED that was consistent with a single temperature, a thin ring-like disk. And the temperature being 95 Kelvin is kind of unusual. It's a bit warmer than we usually see for cold debris disks. So our assumption here is that maybe something is truncating the outer edge of this disk. And the black body radius is about 20 AU. So we're looking for a companion that's at 20 AU. Maybe there's a fudge factor in there, so 20 to 100 AU, perhaps. Instead, what we found is something at 650 AU, which is not all what we expected, and we don't see anything in here. The disk radius is roughly there compared to the star, and we don't see any companions that close to the star. You might say 650 AU seems like a long way away. How do you know it's not just a background star that happens to be projected that close on the sky? And we got pretty lucky. In this case, the system had already been observed by HST several years before, about 8 years before, actually in visible wavelengths, which is again fairly unusual for detections of these low mass companions. And it wasn't recognized for what it was at the time because visible wavelengths do a tremendous job of picking out lots of background stars nearby your target star. So these observations weren't targeted to find planets, they were looking, actually trying to find the disk around the star, although they weren't successful in detecting it. But what we can do is use the relative location of the companion and the star in 2004 versus 2013 to see whether they're common proper motion, whether they're moving in space together with time, and that tells us that they're a gravitationally bound system. So for those of you who like proper motion diagrams, basically what we're showing is the relative motion of the companion to the star versus other background stars to the star. So the important thing to note is that the position of the companion here is very distinct in terms of spatial motion from the 3 other background stars that were in the field. So this just tells us it's not moving relative to the primary star as a background star would. It's staying in roughly the same location in all of the epochs, therefore it's a bound companion of some sort. So what do we know about this system? It's just to recap in cartoon form. We have an SED that tells us that we have a truncated disk where the black body radius is 20 AU, fudge factor could be out as far as 100 AU or so. Because, again, debris disks are quite low density and tenuous, we don't have an image, we only have the SED. So, the best we can do is draw a cartoon of its geometry at the moment. And then we have this 11 Jupiter mass object. So again, I took the age of the system, the luminosity, a model of planet evolution, get a mass. So it's something that's pretty near the cutoff between planets and brown dwarfs. And it's orbiting about 650 AU away. So this raised a number of interesting questions for us. The first of which is, should we name it Gallifrey? There were a few people who thought yes. We had to say no. The rules are rules. And is any press good press? I'm not sure. The jury's still out on that, but I hope we don't have an opportunity to test that again. But on a more serious note, there were some scientific questions that were raised with this discovery. What's the relative inclination of the planet and the disk? What's the geometry of this system? As I said, we don't have an image of the disk, all we have is this SED. We know where the planet is today, but we don't know its orbit, because at 650 AU, that's a 10,000-year orbit. And so 8 years, with the precision of astrometry that we had at the time, is not enough to really rule out any families of orbits with high significance. So it could be a circular orbit, elliptical orbit. You could even imagine the situation where it's orbiting perpendicular to the disk. At this point, we don't know. Although, given a few more years of astrometric monitoring with higher precision with instruments that are designed for this, you can start ruling out some families of these orbits, at least radial versus tangential orbits. So we don't know yet whether this companion sculpts the debris disk. It might be on a very elliptical orbit and truncating the outer edge, or it might be totally unrelated, and there could be an even lower mass planet farther in that's truncated this disk. We can't tell at this point. And I think one of the other really interesting questions that this system raises is, how did this guy form? How did it get there? Why am I calling it a planet mass companion instead of a planet? Very carefully here. That's because it doesn't really seem to fit with the formation models that we associate with planet formation. So if we think about core accretion, the mechanism that formed most of the planets in our own solar system, or maybe even all of them, that's saying that the planet, the companion would form close to the star within the disk, maybe as part of a multi-planet system, and get kicked and scattered out to a very elliptical orbit to where it is today. But there are a few things wrong with that. We don't see any more massive companions in our imaging into at least 35 AU, and it takes a more massive object to kick out a less massive object. But I think even more importantly, if the companion was on an elliptical orbit that went back into the inner solar system, it would cross through the disk, and in just a few orbits, it's quite likely that it would have very dramatically disrupted this disk. And one of the reasons we targeted this system in the first place is because the disk is very bright and massive. So that suggests that it's not disrupted at this point. So we think that this is a less likely scenario. Could it have formed in situ at 650 AU as part of in the outskirts of a protoplanetary disk? Again, this is less likely because typical sizes for protoplanetary disks are only a couple hundred AU, maybe 200, maybe 300, but 700 AU with enough mass to form an 11 Jupiter mass object is hard to come up with a situation where that would happen unless we have a very unusually massive disk, but we don't like to invoke unusual situations. And similarly, could it be captured? Could there have been a free-floating, low-mass brown dwarf in the system that got captured? This is a relatively young stellar association, so 10 million years, roughly. And it could have been captured, but this is, again, something that's pretty unlikely. We think it happens, once or twice per cluster. Do we really want to invoke that in this case? I don't. So my favorite explanation is basically a failed binary star system. So that means that there's a clump of material that formed the primary star and a clump of material that formed this companion. And for whatever reason, either the companion's cloud was small to begin with or it became starved for some reason. It's a failed star. This is pretty unusual. The mass ratio between the two objects is less than 1%, which is unusual for binary star formation. So this isn't a perfect explanation either. The jury's still out, but I think these are fun things to think about anyway. So are gap debris disks good signposts for planets that we can image with current technology? Maybe. We had a fairly small sample size in this case, but we did have one detection, although it's questionably associated with the disk. So it's a little hard to say in this case. I think it's still interesting and worth pursuing, particularly if we have better technology. So if we build better instruments, we could get more sensitive limits. We could look for, instead of being sensitive to high mass planets, we might be able to be sensitive to middle mass giant planets. And certainly it doesn't take a particularly massive planet to sculpt a debris disk. So let's look again back at this contrast curve and step through why better instrumentation would be helpful. So out here, where the contrast curve roughly flattens out, that's just the background sky limit. You're not going to do better there unless you spend a lot more telescope time or get a bigger telescope, just pure collecting area. On the other hand, close to the star, we're what we call contrast limited. In other words, we're limited by our ability to subtract away the stellar PSF. And we can do better there by having a larger telescope with a smaller lambda/d resolution limit, but also a telescope with better adaptive optics, because that gives us a more stable PSF that we can model and subtract more effectively. So, for example, you can compare to a recent contrast curve published from the LBT. And okay, it's not quite fair. I didn't have any data sets that were quite as good in my thesis as this particular one. It had LBT had a bit more rotation, a little bit longer integration, but they're roughly comparable. And this gives you an idea of the kind of improvement we could hope to gain over MMT by using one of the current generation systems. So put a little bit more quantitatively, let's look at one of those really challenging observations that I mentioned before, where we're trying to push to very small inner working angles. With MMT, we were sensitive to low mass stars. But with LBT, or G-Pi sphere, we can suddenly push that down to be sensitive to high mass planets to low to intermediate mass brown dwarfs, which is a huge step forward. And if we compared with one of the contrast curves where we were sensitive to giant planets on the high end, going to LBT would allow us to be sensitive to things much closer to a Jupiter mass. And we do this using adaptive optics. So the quick cartoon picture is that here you have light coming in from your telescope that's been blurred by the atmosphere as it enters. And when you send it to your science camera, you get the classic seeing limited image where the light is smeared over a resolution that's about 1 arcsecond or so. And we're looking for planets at much less than an arcsecond, so we'd like to get to the diffraction limit. So we add a wavefront sensor, a piece of instrumentation that will sense what the atmosphere, how the atmosphere has distorted the incoming light, and can send corresponding commands to a deformable mirror that can counteract whatever aberrations the atmosphere has put in. And so once we do that, deformable mirror counteracts what the atmosphere's done, gives us light that's pretty much undeviated or has a nice flat wavefront, and we get a really nice diffraction limited image. Those are actual images from LBT with AO on and off. So the LBT, as a refresher, is the large binocular telescope just a few hours away from here. It has 2 independent apertures on the same mount. And each one of those apertures has to have its own adaptive optic system because each one of the apertures is looking through a different column of atmosphere. So each one has its own wavefront sensor. And we do this interesting thing where we put our deformable mirrors actually integrated into the telescope here at MMT and Magellan as well. DLT will be doing this in the future. It helps for various reasons, particularly for mid-IR observations. So our system has several advantages over previous generation systems. As I mentioned, we have this excellent deformable mirror with a large number of actuators, meaning that we have finer grain control over the spatial patterns that we put on it. We can better match the atmosphere. It has a large stroke, meaning that just the one mirror alone, rather than a Whooper-Tweeter system, can counteract the aberrations in the atmosphere. We're using a pyramid wavefront sensor instead of a Shack-Hartman wavefront sensor, and that has several benefits in terms of flexibility, in terms of sensitivity over Shack-Hartmans. And we're also running it faster than some of the previous generation systems. The faster you run your control loop, the more quickly you measure and apply corrections, the better job you're going to do correcting the atmosphere. So we're doing pretty well. I showed you those contrast curves already that were quite nice, and here's a beautiful image where you can see a dozen airy rings. But if you look closely at the center and know what you're looking for, this first airy ring is not particularly symmetric. And that's because rather than having the theoretical PSF, on ElmerCam we have sort of this unfortunate cross pattern. It's degrading our image performance from a theoretical limit by 10% or so, which isn't a lot. It still allows us to do really powerful science, but we could improve it. And this is coming from the fact that the wavefront sensor, the light is split off to the wavefront sensor before it enters the science camera, meaning that anything that's going on in the science camera, if there are any imperfections in those optics, the AO system doesn't know about them, so it can't correct them. So this has a real impact for our planetary science because, in this particular image, 3 lambda over d is about half the width of this image. And that's where we'd really like to be pushing in to be more sensitive to lower mass planets closer to their stars. So we want to figure out how to improve the image quality of these very small separations. And you can actually trick the adaptive optics system into doing some of that work for you. So if we have our original image here from our science camera, we can tell the AO system, don't deliver me a perfect PSF, deliver me an image that counteracts what's going on in the science camera. So deliver me a PSF that looks more like this. So it's, the low spots are counteracted by high spots, etc. And that gets us a PSF that looks more like this, a 5% improvement in image quality, which is much closer to the theoretical limit that we should expect to achieve for this system. So this is an ongoing project. It's something I'll be finishing up, working on over the next few months, improving the way that we apply and measure these corrections. And this is really going to be very helpful for LBTI, as well as the other instruments on LBT. They're using a similar technique. And that's really allowing us to do near-infrared science, where our optics have even tighter tolerances than the 4 microns, where we typically use LBTI. So to summarize, for the last 6 years, I've been interested in understanding how imaging can provide us information about the atmospheres and formation mechanisms of giant planets and brown dwarfs. I touched on that a little bit and started out here with those sorts of studies. I thought, well, there aren't too many planets we can do this on, so it would be nice if we had more. So I worked on a survey to find giant planets that are indicated by how they're interacting with the circumstellar environment. And we had at least one success in this case. Only one, but it's a good start for a small survey. And it would be what we need to do to improve upon this is to really optimize the next generation of adaptive optics instrumentation. So I've been working on that with LBTI, and looking forward to doing that with GPI in the coming fall. So thanks very much for your attention. I'll take questions.
Vanessa has invited questions. Anyone have questions?
Done.
I have a question. For your planet that you discovered, Is it possible that it was ejected? In other words, is there another possible model that might get it to the wide separation?
So the problem with ejection is that let's say it formed outside of where the disk is currently. So we don't have this problem with the disk being disrupted. That requires some sort of strong gravitational perturbation. So from an object more massive than the planet. But our detection limits are good enough that we can see equally massive objects all the way into 35 AU, which we think is probably within the extent of the debris disk. I guess you could invoke a scenario where you had a close passage when the cluster was younger and more dense that disrupted it. That's a bit harder to rule out, but I would say that's an unlikely event, but it's a possibility.
Okay, any more questions? Well, I guess everyone, including Vanessa, needs to leave the room, but not the committee members.